Assalamu alaikum and welcome to our channel. I am Dr. Hamad Ismail. Today we will talk about another GROMACS tutorial known as umbrella sampling. Umbrella sampling is a study how molecules like protein or other molecules move apart or come together. During this movement, our goal is to measure the energy changes, which is known as the free energy, as the distance between the two molecules are changes. When the distance is changes, energy is changes. We will going to measure this energy. So let's start. This tutorial can be done on the Linux operating system, or you can use the WSL system on the Windows. On our channel, we have created a series of GROMACS tutorial. In this series, the first lecture is how you can set up your GROMACS on the Windows using WSL system. The complete instruction can be found in that tutorial. Quickly, I will want you to know that how you can use it. First of all, you need to activate the Windows virtualization on your system. After that, you will need to go on the Microsoft Store and type Ubuntu, and you need to install one of these Ubuntu. In current tutorial, I am using Ubuntu 24.04. Once the Ubuntu is installed, you will be directed to this window, or you can find this in your startup window or Ubuntu. To start, first of all, you need to run this command. This command you must need to run this command once in a day. It will find out and update any packages available on the Ubuntu. Then you need to set up the GROMACS. To set up the GROMACS, you need to copy this command and run in the Ubuntu terminal. In the next step, you need to download and compile the GROMACS. In this current version, I am going to use GROMACS 2023. You can use the updated version, just change the name over here in this command. If you are using 2024, you can change it to the 2024 again here and again here. It will download and compile the GROMACS, but make it sure the internet is connected when you are going to run this command. After that, once you have run the command, you need to source the GROMACS. To source the GROMACS, you need to copy this command, paste in the GROMACS terminal and press enter. So it will accept the compiled GROMACS. There is another short software which is known as the GRACE. You just copy this command and install this software in your Ubuntu terminal. It will help you view the graph during the GROMACS tutorial. So this is our GROMACS tutorial for umbrella sampling which you are going to use. So let's start the tutorial. From the tutorial, this is the example we are going to use. They have provided the file. Simply go to this link and download the file. Sorry, it is here. This is the previous tutorial, while here is your file. Click on this one and a file will be downloaded. Simply copy this file and make a folder on this top name as GMX and paste this file in this folder. Once the file is copied, we need to give the path of your folder to your Ubuntu terminal. To make this happen, we need to make two changes. First of all, go to these three dots, go to options, and then in the option go to view, and in the view here is the option hide extension for known file types. Uncheck mark it and apply. We are going to use it in the rest of the tutorial because now it is showing the extension of every file. This is the compulsory part of the tutorial. The second thing, just click on this address bar and copy this address. After copying this address, I came to the window and paste the address bar over here. What you need to do, simply Make the C small. This is my drive. It depends what you got. Either you are using in the D, E or so on. Remove the colon and change all the backward slashes with the forward slashes one by one. And this is on the desktop, and this is my folder in which I am going to work is GMX. And before it, type cd space / MNT /. Now our command is ready. Copy this command and go to Ubuntu terminal and paste it and press enter. You can see now we are in the folder desktop with the name GMX. Type ls to see all the content present in your folder. Right now we have 2bg_model1, that is cap.pdb. This is the file we have just downloaded from this website. You can view this structure in your PyMol. Like this is my PyMol file, open, and in desktop I have GMX folder, and this is my structure. You can see it is a multiple chain protein. You can go to display and sequence mode, display name, 3-letter name, and if you are not showing this line over here, you can click on this sequence. You can see this one is acetyl group, and if you go to the end, this is alanine and so on. You can view in this way. So moving on the next step, we need to run this command. For your ease, we have copied all the command, the modified command. Like when you take these commands directly from this, you may encounter some error. To avoid this error, we have prepared this file, and this file will be available for you to download on our video. You can go to the description section and click on the download file, and you can download all these files. So simply copy this command, go to Ubuntu terminal and paste and press enter. You will be directed into the force field menu. From here we are going to choose 53A6 force field. So we need to type 13 and press enter. Now it is asking to select the water model. For water model we are going to select SPS. So we will type 1. Now it has multiple chain. It's saying that chain 1A is processing. It contains 184 atom and 27 residue. It is asking that select the terminus type A for ACE1. You can see here AC1 is not present, so we are going to type 2 and press enter. Now it's saying select the terminus for starting terminal, the end terminal, alanine 27. For alanine 27 we have carboxyl group, so we will choose 0. The chain 1 is complete. Now you can select for the chain 2. So I will repeat the same process. 2 and 0, chain 3 completed. 2 and 0, chain 4 completed. 2 and 0, chain 5 is completed. You can select, you can see your own protein. If your protein contain the first amino acid as amine, you can choose amine. If your first contain NH2, you can choose NH2. If there is some other acetyl or amine or something more, you can choose none. And for the N terminal, you need to choose the carboxyl group or the other group as per your protein. So you need to choose wisely. Our job is completed. Now if you go to the folder, you can see you have multiple files are generated. From this, go to the file topol_protein_chain.b. Open it with any notepad. Well, I prefer to use Notepad++. It's a small software and it provides multiple features. So just I have configured it with the Notepad++. You can right click on it or you can open it in the Notepad as well. Well, in this tutorial I am going to use Notepad++. Just open the topol_protein_chain_b. Go to the last line of this file and here in the line 1459 type underscore and b. So we are going to fix the b to calculate the difference with respect to the other chains. If we came back to the umbrella sampling, it says that this command is given. Okay, so we have completed this part. Then we need to go to define the unit cell. Once you have changed it, press Ctrl S. It will turn into the green and close this window. The next step is to define the unit cell. Why we need to define the box? For dividing the box, like these are the 5 chains. From these 5 chains we have denoted the B chain as a pulling distance, which means the chain B will be pulled at this position. For being pulled, we need a box larger than its position. If it has a small box, the pulling situation will be not correctly incorporated. So make sure that pulling distance is less than half of the box, which means box size should be double of the pulling distance. Let's say if your molecule can be pulled up to 5 nanometer, you must select the box with the 10 nanometer, which is higher. In this tutorial they have used the z-axis, like in this one, this is the z-axis, they have used the 12 nanometer box, which is same. Let's say the coordinates are 3.2, 2.1 and 2.4 and the box dimensions are double, let's suppose 6 into 5, 4.3, and the z-axis, which was 2.4, we have changed it to the 12 nanometer. And kindly note that these coordinates are chosen manually by considering the protein. You can I just will show you in the VMD that how you can see your protein in a box. If the box condition is changed, you can change manually the size of your box. If your protein is larger, you can go increase this one and also this one. So adjust the box according to your protein, but make it sure that one of the axes in which you are going to pull it, it must be doubled. Now using these dimensions, we are going to run this command. What this command will do, this is edit configuration. It will use the complex.grow and it will make a new box with the center and it will use these direction for the box. So copy this command, go to the Ubuntu terminal and paste it and press enter. The new box is now generated. Now how you can visualize this new box? Simply go to the VMD. VMD is a small software which is a free tool available. How you can install or use the basics of VMD, we have already prepared a video on the demonstration of VMD and analysis. You can refer. If you are new to VMD, you can see that video. The VMD has 3 windows. One is this VMD main window, one is the background window in which the DOS is run, and the third window is the display window. Let me adjust it. Go to the file and click on the new molecule. From the new molecule, go to the browse, and from the browse I will go to the desktop. On the desktop I have folder GMX. In the GMX I have just created the new box.grow. Open this new box and it will show you something like that and load the molecule. When you will load the molecule, you will see something over here that the molecule has been shown. Now come back to the DOS window of VMD, press enter. It will show you the VMD, type PBC space box and press enter. When you type it, go to the display, you will see a box has been appeared. If you can see that we have a long distance with the y-axis, while you can scroll down it with the mouse, or you can use the wheel to make it small or the large. So the x-axis and y-axis are small, but the y-axis is large. So you can adjust your box according to your need of the protein. Let me close it. Just close the window and came back to our window. Now the second step, defining the unit cell, has been completed, and now we will move to the next step, which is known as the solvation step. To solvate the molecule, type this command GMX solvate new box.grow, and we will use the CPC mechanism, and it will generate the solvate.grow and topol.top. So copy this command, go to your Ubuntu terminal, paste it and press enter. The job is completed. If you go to the folder, you can find the solvate.grow. If you open it into the PyMol, you can see that your protein has been solvated. These are all solvent molecules. So click on the sequence and go to the end. You can see these red dots. These are basically solvent molecule. So come back to our next step. For the next step, we need a file. You can click on this one, open it, and this is the file which with the name ins.mdpi. So you need to copy all the content, go to your folder, create a new file, new text file, change its name along with its extension .txt, name it as ins.mdp. Open this file and paste it. To double check the name, Control S, save it. Oh, there is an error in the name, just need to change it. It's now correct. The file is saved. Now copy this command, which is GROMACS, which is using ins.mdp and solvate.grow and topol.top, and it will generate TPR file. This command is for the warnings. Sometime it comes with the warning. To avoid this warning, we are adding this command. Copy this command, paste in the Ubuntu terminal and press enter. The job is completed. After completing this job, we are going to use this command to neutralize the charge, which is either they are sodium or they are chloride ion. So for this we are going to run this command. Paste this command, press enter. Now it's asking that which group you want to run. Here we will choose the solvent. We will choose the group number 13. Type group 13 and press enter, and the command is completed. With this, we have completed this solvation step. Our next step is energy minimization step. For the energy minimization step, we need to generate another file which is present over here. Open in a new window. The name of this file is minimum.mdpi. So I am going to copy this name and go to the folder in which I am working, create a new text file, change the name along with the extension, name it as minimum .mdp and open it. When the file is open, copy this content. From where this content came? From here. Open this and copy all the content and paste in this text file. Press Ctrl S and close it. Now we need to run this command. As when you run this command, it may come with the error, but we have modified to avoid the error. It is using GROM-PP and it will use minimum MDPI, it will use Solvate-IN.GRO and Topol, and it will generate em.tpr. So copy this command and go to Ubuntu terminal, press enter, paste and press enter. Okay, it's giving an error. It says the fatal error is cannot find position strain.grow, and also you can still use the same. Okay, it seems like we have made a mistake during the copying. Oh yes, here is the problem. Here are the two files. One file is the minimization file, this one, and other one is NPT equilibration file. We just used wrongly the equilibration file. Instead, we need to use the minimization file. This is the minimization file. What we need to do, open this file, the minimization file, copy this content, go to your folder, the file you just prepared minimum.mdp, delete all its content and replace the new content with the ins.mdp and save it. After saving it, close it. Now go again, copy this command with the one warning. If you are having multiple warnings, you can change the number 1, 2 or 3. Copy this command, go to again the Ubuntu terminal, paste the command and press enter, and it is done. Now when we have completed this command, for the next step we need to run the energy minimization step. For this we have generated this command, copy command from here, go to Ubuntu terminal and paste it, press enter. It is performing the energy minimization step. It may take 2 to 3 minutes depending upon your computer speed. While it is completed, we need to prepare another file which is npt equilibrium file. We need the name npt.mdpi. Copy this name, or you can simply type it. Create a new file, new text file in your working folder and change the name as npt.mdpi. Press enter, yes, and then open it. After opening it, when the file is open, go over here, open this file and copy all the command. Please check this is the npt equilibration stage. Copy all the content, go to this file, paste the content, Ctrl S, save the file and close it. So for this command we have saved the file. So let us check our command is completed. To the next step, which is generate NDPI. We have already generated it, and now we are going to run this command, which is GROMP, and it is using npt.mdpi and em.grow, topol.grow, and it will generate npt.tpr. Copy this command, go to the Ubuntu terminal and press enter. The job is completed. After the job is completed, we need to run this command. We have modified this command as this one. We added -v. -v will give you the real time then when this command will be completed. So copy this command, go to Ubuntu terminal, paste the command and press enter. The job is started. It will take around 30 to 40 minutes depending upon your computer speed. Our job is completed. Now we want to visualize this. Just minimize this one. This is VMD. For VMD, go to the file, click on the new molecule, go to the browse. From the browse, go to your folder, and in your folder search for em.grow. em.grow. This one is the em.grow, and then open this file and load this file. The file is loaded. We want to change the display. Simply go to graphics, presentation, and in presentation drawing methods, go select ribbons. Use then apply and close. Use your mouse cursor to move it closer or further apart. Then come to this window, go to browse again, then open the file npt.trr. Open this file. It is basically the trajectory file, and then load. When you click on the load, it will load all the frames which we just have generated. Now you can add box. Go to VMD terminal, press enter, then type PBC space BOX box and press enter. Minimize it, and you can see the box is here. You can see this one, and then you can click on the play button. You can see this molecule by this one. It means our work is working fine. So this step is completed. The next step is generating configuration. So we will move to the configuration. So in this step, we want to see the peptide dissociation, which means we have multiple chains like A, B, C. Let's suppose we want to see that how far a peptide A move from the rest of the peptide, especially the chain B. If you remember, in start we kept the chain B as a reference, which means the chain B is static. It is not going to move away, but rest of the chain can move away. So in this case, we are giving the chain A, we want to measure, like chain B is at its position, and we want to see how far chain A can go. Chain B is its original position, and how far chain A can go. For this one, we need to make an index file from npt.grow file. To make this happen, we are going to copy this command, then paste it into the Ubuntu terminal. It will give you option. You can see here are already the 16 groups. We are going to create the new group. The new group number will be 17. You can check your own. If you are at the position number 10, you can create the 11. If you are on the position number 20, you can create 21. So in my case, it is at position number 16. I'm going to the new group, which means R1 to 27. R mean residue. You can find the key over here. Like I'm going to type R space 1 to 27, which means residue 1 to residue 27. I'm going to give it is a name 17 chain A. So copy this command, which means the name space 17. The next group is 17 space chain A. I am going to give it the chain A. The next I am going to group R residues from 28 to 54. I am going to give it the name 18. 16 are present, 17 was chain A and 18 is chain B. You can also create more group. If when you are done, type Q and press enter. To confirm either these groups are made or not, you can again run this command GMX, then press enter. You can see here initially it was 16 group, now the group number 17 and 18 are appeared with the chain A and B. I'm not going to change anything else, so I will type Q and press enter, and then I will be out from this index file. Now we need to perform the pulling mechanism. For the pulling mechanism we need another file. We are done with this one. Now we want to run this command. For this we need another file, which is md_pull.mdp. Copy this name, go to your GMX folder, create a new text file, change the name along with the extension, give it to the name md_pull.mdp, change the extension yes, and I think I have already given. Let me change the name again here, md_pull_.mdp. The name is changed now. Open this file. Now from here on the top, this one here, this is the script file. Open this script, copy all the content from here and then paste into the folder. Let me copy again. After copying, Ctrl S, save the file, then close it. Now we need to run this command. For this one we have modified this command to ignore the warnings. Just copy this command. All these files, the script file as well as the command file, will be available for you in the video description. Paste this command and press enter. It is completed. The next step is running the pulling mechanism. For this we have modified this command. Copy this command, paste it and press enter. Now it is running our pulling mechanism for the 500 picoseconds. Our job is completed. Now we want to see we have generated the file pullx.xvg and pullf.xvg. So you can run xmgrace, like copy this command, xmgrace, and the name which just generated, pullf.xvg, pullx.fvg. Go to Ubuntu, paste this command and press enter. The XM graph will be showed. This is the pull force. As we are running, it's just 10 picoseconds. I think the process has been terminated somewhere in the middle. We need to close it. If you also see the same error, please rerun the same command. I have run it again and completed until the 500 picoseconds command is completed. This sometime happen if your computer got out of battery or disconnected or closed, so the command may terminate in the middle. So you need to run it again, then it will be completed. After the completion you can again run this command. Now I am going to again run this command to see the graph here. Now you can see that my graph is completed. It is now showing the 500 picosecond time. This is the 4 kilojoule per mole per nanometer, and this here it is going at the peak and then is to the back. So now this step is completed. Now again we want to see the pulling mechanism in the VMD. In the VMD, now we will open the file, go to the new molecule, go to the browse. In the browse, search for npt.grow. 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 This one is the npt.grow. Open this file and then load it. It will load the frame. It will show you like this one. Change the graphics presentation from line to choose as ribbons. Apply, close it, then go to this window, press enter, type PBC space box, come back to this window. You can see the box over here. Well, this one I need to switch in this way. Now again go to browse. From the browse, search for pull.xtc and then open this file. This is also a compressed trajectory file. Load these frames. It will load all the 500 frames we just generated in the previous command. These frames are generated. Just let me get it a bit zoom. Then this one is the speed and this is the place button. So you can see over here that this chain A is moving from the chain B. This is covering the distance. So it make our idea success, which means we are going in the right direction. So now I close the VMD. Then we have completed this step. The pulling mechanism, we also completed this step. This was the same interface we just saw. Then we also saw this graph. This is also done. The next step is we need to extract the frame from the trajectory. To extract the frames from the trajectory, we are going to use this command. Copy this command. What this command is? GROMACS trajectory view. It will use the pull.tpr and pull.xtc, which is our trajectory file, and it will generate the configuration.gro file for each of the frame along the 500 frame. We have the 500 frame. It will extract the frame from each one. So copy this command, go to Ubuntu terminal, paste it and press enter. It will ask you what system you want to output. Here we are going to choose the group 0, which is our complete system. Type 0 and press enter. Now it's extracting the frames, like it is now just extracted the 929 frames and so on. It will extract all the 500 frames one by one. This job is also completed. If you go to your folder, you can see that all the frames up to 500 frames have been generated. So our next task is this one, which is to generate the distance for all the frames. For this one, the author of this tutorial has generated a Python script which is available over here. You can copy this command, and this is the name of the file. Copy this name, go to your Ubuntu folder, create a new text file and paste the name over here, same name, get distance.ch, change it, open in the notepad, then copy all the content, paste it and Ctrl S save it. Our command has been saved. What this command do? This command use the 100 of the frames and will calculate the distance from each of the frames. The second method, sometimes this method doesn't work. Why it doesn't work? Because here we are working on the Ubuntu and the file we just generated is generated in the Windows. The other way to do that is copy this command, nano space get underscore distance.ch. Copy this command, go to Ubuntu and press enter. I have just pasted all the content over here. Just give me a demo. If you are using for the first time, you will get it blank. You will get it like this one. So copy all the content from here, go to Ubuntu, and press Ctrl V. It will paste all the content. After doing this, press Ctrl O, then press Enter, and then press Ctrl X. All the content has been copied in this file and they are saved. After saving it, we want to make it executable. For making it executable, we will use this command. Copy this command, go to Ubuntu terminal, paste it and press Enter. Once the command is executable, now we can run the script by using this command // and the name of the sh file. Paste this command and press Enter, and you can see it is now extracting the frame and extracting the distance. It will take a few minutes depending upon your computer speed. They are approximately 500 frames, and it will calculate all the distance and put into a separate file with the name summary.distance_distance.dat, and you will get the distance of each frame in that file. We will have to just complete it, and then we will analyze this file. Distance has been calculated. Now to see the result of distance, copy this command. This is the summary distance dot that has been generated. You can go to your folder and check that this file has been generated. Summary_distance dot. Open this file and you can check the distance of each frame over here. So these are the distances. To check on grays, simply type xmgrays and the name of the file. So I'm going to copy this command, go to Ubuntu and execute it. So you can see that over the passage of time, as the number of frames increases, the distance is being increased as one protein is moving against the other one. So the distance has been generated. Once the distance has been generated, in the next step we will generate the energy, which is our main analysis. With this, we have completed this step of generating configuration. Now our next step is umbrella sampling. For the umbrella sampling, we need to find out the spacing and the distance. Look at this file. If we focus on the number 6, the distance is 0.502, and when we took it on the 26, basically it is become 504. From 502 to 504, it means with every 20 frames the distance has been increased 0.02. Just an idea, we are going to make the difference of 20 frames each times, which means we are going to run every simulation and configuration after every 20 frames, which means one run will start from frame 6 until frame 20, frame 6 to frame 26, then next frame 26 to 46, and so on, which means you need to run the command multiple commands. So we have prepared the command for you. We try to automate it, but whenever we try to automate it, run the Python script, it gives some error, but we will recommend you to simply copy all these commands. For here in the red, this is until frame 446. Copy all these commands collectively. These commands are present. What this command do? It's use GROMACS, GROMPP, npt_umbrella.mdpa, and it is going to use configuration number 6, topol top, and configuration 6.grow will be generated. And this file is using npt named as npt0, and we are giving it to the maximum warning 3, so it will ignore the 3 warning maximum. Before running it, we need to generate a file with the name npt_umbrella.mdp. Copy this file, copy this name, go to your folder, create a new text document, change the name as npt_umbrella.mdp. Please be conscious about the name. If you typed it wrong, it will not execute. The file is generated. Open this file, then go to this page. In this page, this is MDPI file. Open this content, copy all the content, go to this file, paste it, Ctrl S, save and close it. Now our MDPI file has been generated. What you need to do is simply copy all the commands collectively and paste it. It will run the simulation. For this tutorial, we will run only until the file 8 to save the time. Simply for the demo, I will copy all these first 8 commands, then paste it. You can see all the commands are pasted and press enter. The command is started. You don't need to worry about it. This is 100 picosecond time. When the one command is completed, the second will be executed automatically. Depending upon your computer speed, it can take about 30 to 35 minutes to complete the one job. If you are using the CPU, if you are using the GPU, it can be real quick. If you are on the CPU, these 8 commands can take up to 4 hours. The 8 command can take up to 4 hours, about 25 to 30 minutes per job. After completion of this job, we will move toward the next step. The next step is our final production step. We have generated 23 frames. We have generated 9 frames starting from 0 until 8. 0, 1, 2, 3, 5, 6, 7, 8. Well, this tutorial have used 23 frames, but to save the time and to give you a demo, we have generated the 9 frames. For these 9 frames, we now again have to generate the molecular dynamics simulation step. In a similar way, we need to run it one by one again. This time we need this script. For this, first of all, save md.umbrella_mdpi. Copy this name, go to your working folder, create a new text file, change the name along with the extension. Yes, open this file, open this here. This is the MDPI file. Open this file, copy all the content, go to the file and paste it, and Ctrl S to save it. At the line number 7, these are the nano steps, which means every step will be run for the 10 nanoseconds. To save the time, we change it to the 0.1 nanoseconds, which means it is 100 picoseconds. So for doing this, I will reduce 2 0 from it and then save it. It's just for the demo, so I am saving my time. Close it. You can use 1 nanosecond, 10 nanosecond or 100 nanosecond. But for every time, every frame, it will take 10 nanosecond. It is lot of time if you are using the CPU. So if you are on the GPU, then you can use the higher rate. For the demo purpose, I am only using the 100 picoseconds. Close this window, also close this one and close this one. Similarly, we have generated the command for each one respective to the previous frame. You just need to copy all these frames and paste it into your Ubuntu terminal. I am going to copy the first 9 frames. First 8 frames along with the simulation steps. I am going to copy it and then paste it. After pasting it, I am going to press enter and it will be started. Now you can see that our job is started. We have set the time as 100 picosecond, and 100 picosecond can take about 25 to 30 minutes or 35 minutes for one run. You need to run as many as you like to calculate the frames. Our job is completed, which means our simulation step has been completed. Umbrella sampling has been generated. Now we will move toward the data analysis. If you look into your folder, you can see a lot of messy files in your folder present in it. The frame, these are the configuration files, the frames, and so on. There are a lot of things present in it. For analysis, there is a little information available in this tutorial. However, we make it simple to analyze. First of all, we need to generate the list of pull forces file. To do this, we will list the umbrella and pull.xvg to sort out the pull files into dot file, and also the TPR files. First of all, run this command. Go to your Ubuntu terminal, paste the command, press enter, and then paste this command, execute this command and press enter. What this will do, it will generate the list of TPR files and the list of pull files. Now you can run these two files. If you run, you can run them collectively. Copy this command and paste them and press enter. You can see these are the files: umbrella 0, 1, 2, 3, 4, 5, 6, 7, 8. These are TPR files, and these are pull F files. So we have sorted out this file. These are the files of our interest. Now, what is the next step? These are the same example I have put, that you can see the data from here. After this one, we need to make analyze. For analyzing, we are using the WHAM command. It will use all the TPR files which we have just generated, and it will use all the pull files which we have generated, and it will generate the PMF.xvg, and it will generate histogram.xvg. So we are going to copy this command. Let me give it a color to differentiate it. Copy this command, go to Ubuntu terminal and paste it, and the job is completed. After running this command, we have PMF.xvg and we also have PMX.xvg. We are going to run them using the xmgrace command. First, I will show you the result of PMF.xvg. So we are going to Ubuntu and going to paste it, and you can see these are the result of basically PMF and then PMX. Go to Ubuntu and paste it. PMX results are not generated because the data is the frame we used are very small. To make it sure, I think there is something went wrong during the PMF file. We need to run it again. In fact, we are going to run this file again. Paste the command again. Yes, it's doing the right. I think in the previous step it has skipped some information. Now it is taking all the information. Now we are going to run the PMF.xvg again. Going to show the graph. Yes, here it is. This is the graph that is showing that it is going upward. The gap shows that we have used 100 picosecond and we used only 8 frames. That's why the line is not in a common way that it should be. If you run the complete simulation, you will get a standard curve over here. So these are the graphs. The last thing we can check, it has generated the PMF.xvg and it also generated histogram.xvg. We have not generated a PMX in this command. Now we are going to see the graph of histogram. Copy this file, command, paste it in the Ubuntu terminal, and you can see a peak over here. Rest of the peaks are hide in this one. Let me demonstrate that how you can see rest of the results. If you go to your working directory and search for histogram, it will come as xvg. Copy this file and I'm going to separate it, place it on the desktop. If you open this file, you can see different frames over here. These are different frames. These are all 9 frames we used. If you have used more frames, you will get the more values. Now how to plot these values? For this we are going to use Excel. Open an Excel sheet. Go to the file, open, from the browse menu, go to desktop, and at the desktop select all files. Here you can see there is a file with the name histogram.xvg. we just have placed. Open it and select delimited, press next, then press space, press next, then finish. You can see these value over here. I just simply remove these rows. I don't need them, but I need these one. Select these columns, go to insert and the chart and this scatter chart. You can see these lines. Let me refine it a bit. Double click on it and you will get the axis position. Go to the last, then select the number, and from the number change scientific to the journal. Similarly, click on the y-axis, go to the last, change scientific to the journal. So it will give you an idea. Let me zoom it a bit. That the graph is showing from this position. So double click on it and again, and this is minimum and maximum. We should start it from the 0.45 and we should end it at 0.80. You can see this is the graph at which different frames are moving apart from one to the other position. If you think this frame is this frame has moved mostly and this frame moved rather less than this one, but these frames are close together. If you want to see the more closer look, you can change the frame position from let's say from 8 to 6. You can see the difference. If you even want to see this area how they have moved, just change it to 5.3 and you can see even this one we can change it to 4.7. So this is the difference how they are moving apart. This one is the standard and other rows are moving across. In this way you can see that how different chains are moving with the reference to the standard chain. But don't forget to save this file. Go to the file and click save as the desktop and save it as histo and change the name as Excel sheet. Otherwise, if you don't save it and you just simply close it, it will be disappear and all your work will be gone. So the graph I just show you, it was a brief picture of this graph. As I have chosen the smaller number of simulation and smaller number of frame, that's why I didn't get exactly the same, but the idea is more or less in the same way. If we run the PMF graph, you can see here the peak value, this one 2, is basically your delta G energy. Our delta G energy of graph is approximately 2.3 to 2.4. The reason this is why, because the graph is distorted, because we use only 9 frame and we run the simulation to 100 picosecond only. If you use all the complete set of frames and use 10 nanosecond frame, you will get exactly the same graph with the energy, delta G energy approximately 46 kilojoule per mole. So this is the interpretation. For the interpretation, you can see the little variation is expected. If you still have the variation, you can increase the number of frames, you can increase the number of your simulation time to get the better result and better sampling position. Now if you have done the complete frames and complete time, you will get the value about 46 and the reported value is 50.5. How to understand this? This is the basic thing. Well, when we use umbrella sampling, we are trying to find that how much energy it takes to separate two molecules. Like if a ligand is bind with the protein and you want to know that how much energy is required to separate the ligand from the protein in a specific coordinate. And this is done by calculating the PMF. What is PMF? PMF is potential mean force, which tells us that how favorable and how unfavorable the interaction and the difference is. In this tutorial, we have calculated the value of 46 kilocalorie per mole, which means this amount of energy is required to move a molecule from bound state to unbound state, which means if they have a protein and ligand, to separate the ligand from the protein, they need the energy of 46 kilojoule per mole. But the experimental energy which was previously calculated was 50.5, which is very close to the results. Then how this problem can be covered? You can run the longer simulation or you can run the more frame. Like in our case, we use the difference of 20 frames. You can use the difference of 10 frames or 5 frames, even one frame can be run if you have a good system. If you do that, you will get the better result and you will get the most accurate result, that how umbrella sampling effect and how the ligand and protein move, how the energy is affected. So this is all for today. If you have any question, please write in the comment section. Please like and subscribe our channel for more videos on the GROMACS and molecular dynamic simulation. Thank you so much for watching. Allah Hafiz.